You know how you can instantly tell if a video is like a proud parent filming their kids' first steps?
Ooh,
Even if the
definitely.
camera's all shaky, you
Yep.
feel that energy. Or think about Hitchcock, right? That dolly zoom effect.
Yeah, the way it just makes your stomach drop a bit. It's powerful.
Exactly. We have this kind of built-in ability to understand not just what we're seeing, but how the camera's moving and what that tells us.
It really does speak to how deeply we're wired for, well, for movement and perception. They're linked. And camera motion in video is just such a perfect example of that playing out.
Right. And that's actually what we're diving deep into today.
Mm-hmm.
This whole fascinating world of camera motions in video.
Mm-hmm.
Our main source here is this really interesting new research paper. It introduces a detailed study in this brand new resource they're calling CameraBench.
Yeah, this paper gets into something that feels really basic, but is often kind of overlooked, how we actually interpret the camera's movement and all the information that comes with it. And it lays out, how they built this CameraBench dataset and the whole rigorous process behind it.
So our mission for this deep dive is basically to unpack how we as humans perceive these movements and then how well AI currently stacks up.
Right?
We'll explore this new way they came up with for categorizing motions.
Hmm.
And this is cool. They worked with actual cinematographers to do it.
Which makes so much sense. Get the experts involved.
Totally. And we'll see how current AI models handle something that honestly feels so intuitive to us. It must be a huge leap trying to translate that human gut feeling into like data points a machine can learn.
Oh, absolutely. Because when we watch a video, it's not passive, is it? We're subconsciously tracking what the paper calls the invisible subject.
The camera operator.
Exactly. Their movements, they're framing things for us, guiding the story, shaping how we feel about what we're seeing.
Think about those examples again. That shaky camera following a toddler. You almost feel the parent's excitement, right?
You do.
And then the Hitchcock dolly zoom.
Yeah.
You mentioned that vertigo feeling. The camera moves in, the lens zooms out, keeps the person the same size, but the background just warps. It's so effective.
Super effective. Or think about Spielberg in Jurassic Park, that slow pan up.
Oh, yeah. Revealing the dinosaurs.
Exactly. It builds that sense of wonder, that awe. Or like Nolan using a camera roll in Inception to visually show that shift in gravity. It makes you feel disoriented with the characters.
Right. And even in video games, like Zelda, maybe a pedestal shot moving straight up, taking you from a close view to this huge landscape.
Yeah, signaling adventure. Or even just, the selfie arc. We've all seen that. Swinging the phone around to show yourself and where you are.
It just hammers home how cinematographers use these moves deliberately. They're storytelling tools, adding emotion, adding meaning.
Yeah.
Way beyond just showing you what's there.
Mm-hmm. Which makes it really interesting to contrast our sort of natural ease with this against how hard it can be for computers.
Okay, yeah. Let's get into that.
So you have these traditional computer vision methods, things like structure from motion or SFM,
Right.
and then the newer big video language models, the VLMs. They tackle this problem very differently.
So SFM, that's more about figuring out the 3D layout of the scene and where the camera went by looking at how things shift between frames.
Pretty much. They try to reconstruct the geometry, but the paper points out they can really struggle when there's a lot going on in the scene itself, lots of independent movement.
Ah, so it's hard to separate out the camera's movement from like a car driving past or people
Yeah,
walking.
exactly. They're trying to build this 4D map, space and time, camera path. Works okay in static scenes, but real videos are messy.
And they probably miss the why, right? Like, why is the camera moving that way?
That's a key point. They miss the semantics. Is it tracking someone? Is it a reveal? That higher level understanding isn't really there.
And even these advanced AI systems, the ones that handle video and text, their grasp of camera motion specifics hasn't really been deeply tested before this.
Apparently not. Not in this focused way. Which leads us to some fundamental challenges in just describing camera motion for a computer.
Okay.
One big one is ambiguity. Without a fixed reference point, things get tricky. The paper gives a good example. Camera looking straight down, moving forward.
Okay.
From the camera's view, it's getting closer to the ground. So is it moving forward or downward? Humans might say following the runner, even if the camera is technically dollying backward to keep them framed. It's context dependent.
Ah, I see. And then there's just the language we use. People mixing up terms.
Oh, constantly. Zoom and dolly are the classic ones. People say zoom in when they mean the camera physically moved closer.
Right, but they're totally different. A zoom just changes the lens.
Exactly. It changes the field of view. Things get bigger or smaller, but the perspective, the relationship between near and far objects, doesn't shift in the same way.
Whereas a dolly actually moving the camera,
Yeah.
that does change the perspective. You get that parallax effect.
Precisely. Closer things seem to move more against the background as you move. And like the paper notes, videos online are complex. You might have a smooth pan that suddenly whips back. Simple labels often just don't cut it.
Okay, so it's complex. How did this research team try to fix this for computers? This CameraBench taxonomy sounds key.
It really is. They saw the need for something much more precise and, crucially, something grounded in how humans actually think about this stuff.
And that's where the cinematographers came in.
Yes, exactly. They collaborated with professionals, people who use camera movement as part of their craft every day. Their expertise, their specific language was vital for building a taxonomy that's accurate and avoids those common ambiguities.
So what are the main parts of this taxonomy? You mentioned reference frames.
Right, so 3 key reference frames. Object-centric, ground-centric, and camera-centric. That helps clear up that forward versus downward kind of problem. Then they use proper cinematography terms. Things are categorized into steadiness, like is it static, smooth, or shaky? Translation, that's your dolly, pedestal, truck movement.
And out, up, down, side to side. Got it.
Exactly. Then rotation pan, tilt, roll, intrinsic change, mostly zoom, and then object-centric moves, like arcing around something or different kinds of tracking shots. There's a great diagram, figure 2 in the paper, that lays it all out visually.
And building this wasn't just a one-off thing. They refined it over time.
Oh yeah, it was iterative. Over 3 months, they were constantly annotating diverse videos, getting feedback from both vision researchers and the cinematographers, and tweaking the taxonomy. That back and forth was crucial to make sure it worked in practice.
Okay, that makes sense. But then getting people to use this detailed taxonomy consistently to label videos,
Yeah.
that sounds like a huge challenge in itself. How did they ensure quality?
That was clearly a major focus. They used what they called a label-then-caption approach. So first, the annotator decides if the motion in a shot is clear enough to label directly using the taxonomy.
No.
If it is, they label all the different aspects, translation, rotation, etc. But if the motion felt ambiguous, or maybe different parts seemed contradictory, they could specifically mark, "I am not sure," for that aspect.
So they're not forced to guess.
Exactly. Those uncertain labels were then filtered out for those specific questions in the final dataset. It prioritizes accuracy over just having an answer.
Smart. And what about movements that are too complex for just labels, or where the why is important?
That's where the second part, the captioning, comes in. For those tricky cases, or just to add context, like the camera dollies in to really focus on the character's reaction, or it pans across to show the scale of the place, annotators wrote detailed natural language descriptions.
So you get both the structured labels and the richer descriptive context.
Precisely. It captures more nuance.
And they didn't just use, like, movie clips, right? They aimed for variety.
Huge variety. They deliberately gathered videos across genres, types 2D, 3D, synthetic, real-world, different points of view, different cameras, even videos with visual effects. And importantly, they manually cut the videos into individual shots first.
Not relying on algorithms to detect shot changes.
Right, because automatic shot detection can be unreliable, especially with complex camera work. Manual segmentation meant they knew the annotations applied correctly to one continuous camera movement.
And then the people doing the annotating, they weren't just random folks, were they? There was training involved.
Oh, definitely not random. They did a whole human study first, with over 100 people, some with professional cinematography backgrounds, some without.
And the pros were better at it.
Significantly, yeah. Figure 4A in the paper shows the experts had much higher accuracy on identifying the motion types. It really proved the value of that specific knowledge.
Okay.
So to get reliable annotations at scale, they set up this really intensive screening and training program. We're talking detailed guidelines, video examples, explaining tricky edge cases, lectures, 5 rounds of exams with personalized feedback. You can see the score improvements in Figure 4B, and they kept monitoring performance. The average person spent something like 20 hours just in training.
20 hours.
Yeah. Only the ones who passed that whole process actually got hired to annotate the main CameraBench dataset.
That's some serious dedication to data quality. Okay, so now they have this amazing, carefully annotated data set. What do they do with it? Test out the AI models.
Exactly. Time to see how the current state of the art stacks up. They tested various models, those SFM SLAM ones we talked about.
The geometry-based ones.
Right, and a bunch of the big video language models. They tested them on different tasks, just classifying the motion type, matching videos to text descriptions of the motion, getting the AI to write descriptions, and even answering specific questions about the video and its camera work.
Okay, so how did the SFMSLAM methods do? Did CameraBench confirm they struggle?
It kind of served as a reality check, yeah. The classic SFMS LAM methods really had a tough time, especially with dynamic scenes or low parallax like. If the camera is just sitting still or only rotating, they weren't great even at basic motion classification. Newer learning-based ones, like this MegaSam, did better in dynamic scenes and generally outperformed the older methods like GoreMap. But they still sometimes got confused. They'd mistake object motion for camera motion or vice versa. Figure 7 shows an example, a lead tracking shot, where the camera follows someone, but the background doesn't have much texture. MegaSam got the camera's backward motion wrong. So CameraBench really highlights where these geometric methods need to improve.
Okay, so SFMSLAM has limitations. What about the video language models? The ones that understand text too?
Well, interestingly, the generative VLMs, the ones built to create text or other outputs, seem generally better at grasping the meaning or semantics of camera motion compared to the discriminative ones, which are more geared towards classification.
So the models that can describe things might have a better feel for what the camera's doing and why.
That seems to be the suggestion. Their ability to reason and generate descriptions might help them understand these more nuanced concepts.
Which naturally leads to the next step. What if you specifically train one of these generative models on CameraBench data?
Exactly what they did. They took a powerful generative VLM Quen 2.5 VL and fine-tuned it using some of the CameraBench data.
And did it help?
Big time. They saw huge improvements, sometimes like double the performance, across both classification and generation tasks. This fine-tuned model actually matched the overall classification accuracy of the best SFMS-LAM method they tested.
Wow.
Though it's worth noting some rare motions, like camera roll, were still tricky, probably because they just don't show up as often in the training data.
Makes sense. And you mentioned video question answering tasks earlier, going beyond just naming the motion.
Yeah, these VQA tasks were designed to test deeper understanding. They required reasoning about objects, logic, not just camera movement, 9 high-level skills, 81 specific subtasks. Figure 6 gives you a flavor.
And how did the models do there?
Standard open source VQA models really struggled, but the fine-tuned Quen model, it did really well again. It suggests that training on this camera motion-focused data actually improved its broader video understanding capabilities too.
That's really interesting. So fine-tuning didn't just make it better at camera stuff, but at video understanding generally.
It seems so, at least based on these results. And the improvements showed up elsewhere too. The text descriptions of camera motion it generated were much better. Figures 8, 9, 10 show examples. And it was much better at matching videos to the right text descriptions in retrieval tasks, as you see in Table 4.
Okay, so let's zoom out a bit. What are the big takeaways here, the main contributions from this research?
Well, first, they've given the field this really carefully constructed taxonomy for camera motion, built with cinematographer input. That's huge.
Right, a common language.
Second, a proven, rigorous way to annotate this stuff and train annotators, ensuring data quality. Third, CameraBench itself, a large, diverse, meticulously labeled dataset. And fourth, a solid benchmark evaluation showing where current AI stands, both the geometric and the language-based models, and highlighting their strengths and weaknesses.
And they also pointed towards what's next, right? Future research directions.
Absolutely. They mentioned things like exploring other ways to train these VLMs, maybe focusing specifically on learning those rarer motion patterns, figuring out the best way to prompt these models,
Okay.
expanding the data to cover even broader video understanding tasks, and maybe the most interesting bit, finding ways to combine the strengths of SFMS-LAM, the geometry stuff, with the semantic smarts of the VLMs.
Getting the best of both worlds.
Potentially, yeah.
So wrapping this up, it sounds like something that feels super simple to us, just watching a video and understanding how the camera moves, is actually incredibly complex under the hood.
That's definitely a key message. We do it effortlessly, but replicating that understanding is a major challenge.
And this work really highlights how valuable it is to bring in actual human expertise, like from cinematographers, to define these things properly.
Couldn't agree more. That human-centric approach to building the taxonomy seems critical.
And ultimately, having really good focused data, like CameraBench, seems to be the key to pushing AI forward in understanding video more like we do.
It really seems to be. This feels like a solid step towards AI that can grasp the subtle language of visual media, which could be useful for all sorts of video applications down the
It
line.
really makes you wonder, doesn't it? Given how much camera motion affects how we feel and what we understand when we watch something,
Mm.
what's the next big hurdle for AI in truly getting the art of visual storytelling?
That's the million-dollar question, isn't it? And for anyone listening who wants to dig in further, the researchers are making everything open source. The data, the models, the code, the taxonomy, the training guides, all the analysis, it's all going to be out there.
Fantastic. So people can really explore it themselves.